All right, so we'll just get started on the Dryden Transect update for you guys. So my name is Ben Frieman. I'm a postdoctoral fellow at Laurentian University in the Mineral Exploration Research Center, and I am one of the lead researchers on the Dryden Transect area. So to start, I just like to show this figure. So this is a compilation that Stefan put together, basically comparing districts by looking at the known gold grade tonnage from them. So basically, let me click on my laser pointer. So basically, this is Kalgoorlie, Kambalda, and Timmins and Dryden camps all plotted together. And what we can see is the Timmins and Kalgoorlie areas tend to have much larger deposits. Of course, a lot more known smaller deposits, whereas in Dryden, there's a lot less known. So there are some historic mines and some decent sized deposits that are going into development here, like Goldland and Goliath. But on the whole, there's just much less known gold in the Western Wabigoon. Of course, this is a fundamental research question of metal earth. Why is that the case? Is this just a lack of exploration? Is there fundamental differences in the deformation histories between these domains? Is there really fundamental differences in the lithospheric evolution and architecture that may or may not relate to differences in geodynamic settings? So I'm going to try, or all of these. So basically, I'm going to try and touch on especially these three topics here today by showing you some of the newer results we have. Due to time limitations, I won't be able to go into great detail. Of course, we know there's all the Abitibi study areas. Of course, you've seen a lot of those this morning, whereas the Western Wabigoon, there's much less known gold. So you just heard from Jujana in this area, and then the Dryden Transect area is right about here. So what did we know going in? You heard some of what Jujana just talked about in this area. So of course, in the late 90s, early 2000s, there was a lot of excellent work done by Kirsty Tomlinson from neodymium and geochronology, basically, which really started to paint this picture of what we thought the terrain architecture was, which is basically that there's this Winnipeg River terrain here, which is characterized by gneissic plutonic rocks that have much older model ages, greater than 3.1 in this map. There's the Marmion, which is an old Mesoarchean, but not quite as old as the Winnipeg River from what we could tell. And then there's the Western Wabigoon, which is, of course, more juvenile looking belts that's purely Neoarchean in age and looks a lot like the Abitibi in terms of its stratigraphy and geochemical signatures. So this was sort of what we knew going in, that there was a bit more complexity as compared to the Abitibi subprovince. But as you can see, especially in the central area here where the Dryden Transect is, there wasn't a ton of this data, and we didn't really know to what degree this terrain architecture held in the Wabigoon. So I'm just going to zoom into this map here real quick. So this is primarily where I've been working. It's not like there's no deposits like you saw from the compilation. There are some more developed prospects and deposits like Cameron Lake, Goliath, and Goldland. These are mostly orogenic gold or maybe mixed in the Goliath case. You'll hear from Chong on his work in Sturgeon Lake. There's this historic BMS mining camp here. There's, of course, a really good-sized deposits along this big structure in the Marmion and Hammond Reef. And then there's basically nothing in the central part of this domain. So like I said, the Winnipeg River is a bit older, mostly gneissic plutonic rocks, as you can see from this map. Western Wabigoon is purely Neoarchean and contains a lot more of these juvenile volcanic successions and synvolcanic plutonic rocks. And the Marmion is has a bunch of Mesoarchean ages, but also a lot of Neoarchean reworking, but also dominated by gneissic plutonic rocks, although there are some well-known volcanic rocks you'll hear from the Atikokan people on, I'm sure. So again, it's really the stratigraphy on the whole within the Western Wabigoon is not that different from the Abitibi. There's all this subsea floor or seafloor volcanism and placing all these volcanic successions. There are sort of porcupine-like deeper turbidite successions here in the gray. And then there's these youngest sort of so-called Temiskaming-like alluvial fluvial to shallow marine successions, especially here in the Stormy Lake group is one of these classic ones. But then sort of conspicuously, there's these older rocks of the Winnipeg River and Marmion. We didn't really have a great sense of exactly what their relative structural relationship and contact relationships were. So some of this work was getting at that. So today, like I said, I won't be able to go in great detail on all these sub-projects, but first I'm going to show you some exciting new data we got from the Winnipeg River subprovince. Then I'm going to talk to you about some of the student-driven investigations here in the central part, particularly on the structural history and timing of mineralization in those domains. And then I'm going to show you some of the work that I've done down here, trying to get at the broader architecture and potential reasons for the lack of gold in this area. And then actually I'm going to sort of finish on what me and Stefan are working on right now, which is sort of putting all this together into a broader architectural model to explain some of the differences in endowment. So yeah, like I just said, I'm going to try and establish the structural setting, timing, geochemical signature of the orogenic gold in the Wabigoon. And then we're going to talk about some of the broader lithotectonic evolution and crustal-scale architecture and those influences on metallogenesis. And I'm going to show you a lot of the regional to outcrop-scale mapping, some of the petrography, paragenetic constraints, and then a bunch of laser ablation data we've done for isotopes of different uranium, lead, and lutetium hafnium primarily, but also the trace element data that goes along with that, some whole rock data to get at some of the alteration signatures and things, and then show you some of the seismic data in particular that we're putting together. So many of you know this, but for those of you who don't, we are a rather big group in the Dryden area. So me and Stefan are the lead researchers. We have, Stefan has a PhD student who you'll hear from on Friday, I believe, about her work. She's been doing some really interesting stuff. She submitted her first paper. We have a set of master's students. David and Amo are sort of finishing their discussions and their thesis right now. Luckily, they had all their data pre-COVID, so they just need to synthesize this. Kendra graduated last year. She's now going to be going up to Snow Lake to work with Kinross this summer. Then we had a really big group through the years of undergraduate students who did a lot of great projects with us. So we had Lauren and Jordan here, who I'll show you a bit of their work. So Lauren's working with Kinross as well now. And a bit of work from Kat Holt, who's now doing a master's degree at UBC Okanagan, and then a whole other series of them that did great work for us. Okay, so first I just want to show you these results from the Winnipeg River, mostly because they were rather surprising and they actually are starting to paint a better picture of why the western part of the southwestern Superior is much different. So this is this Cedar Lake gneiss complex area. And in part, we went here because some of the oldest ages in the entire region come from this area. So back in the 80s and 90s, Corfu and Davis and people started finding these Mesoarchean ages about 3255 in the Cedar Lake gneiss complex. And it's a really complex structurally domain. There's these gneissic plutonic rocks, but they're all structurally interleaved with some supercrustal successions. So there's like BIFs and paragneises in here. And then these are all intruded by Neoarchean aged intrusions of the Lount Lake batholith. So I'm just going to show you results from this one sample here because and a lot of the detailed work I did because they're rather surprising. It's not maybe doesn't look too crazy in outcrop, I guess. It's banded granodioritic gneiss. But the really interesting results come from the Zircon Systematics. So basically, the zircons show very complex textures. There's a lot of xenocrystic cores, various overgrowth domains you can see here. But the ages are really old. So basically all the xenocrystic cores are clustering around 3550 to 3530 MA. These look like a magmatic protolith. They have much higher thorium-uranium ratios as opposed to the younger, more Mesoarchean ages we get out of it that have a little bit younger thorium-uranium ratios. And what I'm showing here is the oldest subset of the results. And I've just calculated in various ways different weighted mean average ages that have low MSWD. And again, I'm just showing this because we get 3530, 3540, 3550 out of this. So we're interpreting this as actually a Paleoarchean protolith. It looks pretty clear. And again, this is really important because the oldest ages are the ones you just saw from the north of this particular sample, which were about 3,300, although they had pretty evolved signatures in terms of their lutetium hafnium isotopes that suggested there was older rocks around, but no one had ever documented them. And so now this is the oldest known rock in the entire southern superior of Canada. They're comparable to stuff in the Minnesota River Valley. Oh, but before I show you that, I just want to show you the hafnium isotopes. Again, because they're really interesting, and they also suggest something about an earlier prehistory. So we see that protolith defines this slightly enriched signature in the hafnium isotopes at about 3550 or so. There are some younger magmatic looking signatures here still in the Paleoarchean, and then these Mesoarchean reworking events defined by these lower lutetium lower thorium-uranium, ratios. Interestingly, you can calculate the model age in various ways. So I'm just doing a linear projection here, basically, which gives you about a 3620. These are probability diagrams for your corresponding to these three different groups for each individual analysis that give us a really nice sort of peak in the model ages here at about 3,600 or so. So it looks like not only do we have the oldest rock in the Southern Superior, but it's providing some indications that it was derived by the melting of a precursor crust that's about 3,600 in age. So getting into the Eoarchean. These zircon grains also have really great trace element signatures. I have a lot more results I could show you, but this is just a nice example from the uranium, ytterbium, niobium, ytterbium, and these kind of Pierce style plots for zircon, comparing the compositions to those predicted from the mantle array relative to the mantle array. And the oldest age populations cluster down here right near the mantle array, suggesting that they were derived by the melting of some maybe like a plateau-like succession. So they show a pretty close spatial relationships in terms of this plot as being derived from something that's more like a OIB-like crust or a volcanic plateau-like succession. And then, of course, you can really see nicely this further differentiation of this felsic crust during the later Paleo to Mesoarchean. So I started thinking about, okay, is this, how does this relate to what we know of the global history in this time frame? So I did a big compilation of a bunch of the results from around the world. And we knew in the Minnesota River Valley. So what I'm plotting here, these are outlines for the probability density distribution from compilation data. So the darker colors are the 68% of the data set. The slightly lighter are 95% of the data. And then, of course, 100% of the data. So what I'm comparing here is to the Minnesota River Valley subprovince to the south, which has a very similar sort of Paleoarchean age. So maybe unsurprisingly, the Minnesota River Valley and this part of the Winnipeg River have a pretty similar looking history. But what was surprising was, looks like also the Cap Falls, Zimbabwe, and Pilbara and parts of the Indian cratons actually have a very similar history. So it looks like all of them have their origin here right around 3600 in the late Eoarchean, and then really evolve towards stabilizing more of crust in the Paleoarchean. So at the very least, it looks like this part of the Winnipeg River formed at the same time as other places globally, but there is the possibility that maybe all of them formed together, maybe a really early supercontinent or something. So that's a bit more speculative, but at the very least, it looks like the Southwest Superior had its origin at a very similar time to these better preserved and exposed parts of Australia, India, and Southern Africa. Cool. So now I'm going to move on to more of the Neoarchean history and focus on the metallogenesis with some of the work we've done. So the Winnipeg River does have a big Neoarchean overprint that I didn't really talk about in there, but it was sort of thrust over the Wabigoon and the Neoarchean. And that's when we really start localizing along these major regional deformation zones that were pretty well known in terms of the regional extent. And so we're going to zoom in here to some of the work Kendra did with us. So basically, this is Kendra's map from her thesis. So these deformation zones form these big high strain corridors. The long and short of it is they're similar to what Jujana was talking about. We have this north-south shortening that transitioned to these shear events, depending on the orientation of these major structures. The Wabigoon deformation zone records this dextral shear. The Manitou to Norwich deformation zone actually records more of a sinistral shear. And this Mosher Bay Washabegama in this more east-west orientations, this dextral shear. And so you can see big clusters of the gold occurrences here, particularly at the Goldland deposit, this Van Horn prospect, and down here in the Ken West Gold Rock area. We wanted to get a better handle on exactly the timing of the, we sort of knew that the gold was coming in broadly synchronous with these shear events, but we wanted to get a better handle on the style of mineralization and relative timing. So I'm going to show you some of the work first from Van Horn, then we're going to go up to the samples from Goldland and Ken West that Kendra worked on. So at Van Horn, there's an active exploration project here in a joint venture with Kinross. There's some great outcrop stripping. So we had the undergraduate students map these in great detail. So this is the lithologic map that Lauren produced with the help of some drone imagery. Basically, it's all pillow basalts and intermediate volcanoclastic rocks. But you can see she outlined several generations of veins, which host the gold in some of these shear structures. There's a bunch of alteration, of course, associated with it. So Lauren was tasked with sort of trying to tease apart this vein history. And basically, the gold is coming in with these intermediate generations of veins, as well as a lot of the alteration. And then they're sort of cross-cut by these later veins. The other undergraduate student here, Jordan, did sort of a complementary project in which he was tasked with more characterizing the alteration style based on some of the geochemistry. So he delineated at outcrop what he interpreted as the highest intensity of alteration. We took a bunch of samples of most and least altered rock, especially in the adjacent to veins and more distal, to do mass balance calculations. So this is just some of the results of one of his particular samples. And of course, what you can see here is we see notable enrichments in gold, silver, tellurium, sulfur, carbon, lead, tungsten, moly. There's slightly different signatures depending on which host rock lithology this is in. But this is, of course, really just a classic signature of enrichment that you might see in orogenic gold deposit of any age worldwide. So it looks like really classic orogenic gold style mineralization, although, yeah. So there's, we have a lot of ongoing work still here. We are still looking at some of the We're still looking at some of the mineralization in a little bit more detail. So this is an example of a pyrite that's cross-cut by, so this pyrite's interpreted to be a little bit older in the volcanic rock, but it's cross-cut by these quartz carbonate veins. And what's really cool is if we zoom in on this little area here, we actually see native gold in direct textural association with xenotime, like Jeff was talking yesterday. Xenotime is a great mineral to try and date by UPB methods. And so this is a great example of what Ross was talking about. You need to know exactly, you need to do this work to find these textual associations to be pretty confident that if we date this xenotime, we can date this gold emplacement event. So although we haven't obtained the date here yet, we did have some great results from the regional work, which was part of Kendra's thesis. So she has samples from Goldland was nice enough to let us sample up there, as well as Ken West in the Gold Rock area. And here's some of the micro textures. Basically, this is monazite in this case with calaverite, electrum. So at Goldland, the paragenesis was pretty well defined by some really great prior thesis work. So the monazite and xenotime has pretty great textural associations there. Whereas at Ken West, it was a little less clear. We do have xenotime, we do have gold, but it's locked up in the pyrite. And there's not as clear as a direct textural association. And that kind of bears itself out a bit in the results of the dating, which I'll show you here in a second. So Kendra got sort of three distinct age populations at Goldland. She got this 2665 age, this 2634, and then more of a 2590. Whereas at Ken West, we really only got this one population from that matrix xenotime here at about 2580. We had her compile up as much of the dating of mineralization as we could from the Southern Superior. So here's a broader age from at Red Lake, from Titanite, which is a little less accurate. In the Wawa at Hemlo, there was some ages about 2671 to 2632. And then from sort of west to east here, Dome, Garrison, Malartic, Camflo, Sigma, Lamac, the ages sort of cluster around this 2660 time. And then there's some younger ages that look like either more of a resetting or overprint in scheelite and rutile that are a little bit younger. So we were actually kind of surprised by this because what we interpret this to mean is that there's a really big gold fluid flux event at a similar time across the whole Superior Province, Southern Superior Province, as well as a younger sort of remobilization event that overprints that at a very similar time. So although the deformation itself is slightly older in the Wabigoon, actually it looks like the gold flux events, fluid flux events, are at a similar time across many hundreds of kilometers of the Southern Superior. So we don't know yet. Again, there's ongoing work at Goliath as well as Van Horn, where we're hoping to get some ages. So we might speculate that those ages come in at this time, but that's, again, ongoing work. Okay, so that's kind of a quick and dirty summary of some of the Winnipeg River work as well as the student-driven investigations. And just to summarize that for you, again, there's some pretty classic looking orogenic gold style mineralization associated with these brittle ductile deformation zones. Sort of surprisingly, the fluid flow events appear to be at a similar time to the Abitibi subprovince. And there are really prospective zones that occur along this Wabigoon and Manitou to Norwich deformation zones, but along that Mosher Bay Washabegama deformation zone, and particularly in that south central part, there's much less known gold. So my work was I've been trying to sort of constrain the broader architectural controls. So really quick, again, I've shown some of this before, and if you, I'd encourage you to watch my PDAC talks where I go into a bit more detail. But the point here for today is basically I did a bunch of sampling for zircon. There's this Neo-Archean intrusion here, and I sampled a bunch from the northern part of the Marmion. We weren't really sure if it was Marmion. And the long and short of it is, although this is a Neo-Archean intrusion, there's a ton of inheritance that looks quite similar to the signatures you get out of the Marmion subprovince. So this is backed up by the hafnium isotopes. So what it tells us is that we thought that there was underlying Marmion crust, We, of course, do have the seismic here, which we interpret to show this gneissic plutonic crust, and sort of the intrusion would be right about here. So what we think is the southern part of the area has a bunch of this older, multiply reworked crust below it. So this, of course, will have big implications for the metallogenesis, because that crust is going to be much more dry and reworked. So we think, at least in parts of the study area, there's a more limited gold availability, and that's the boundaries of which are marked by these big lithospheric scale structures, which might have a longer history. So things like the Manitou de Norwich or the Marmion deformation zones are these sort of translithospheric structures that are sort of separating more juvenile crust from this older material that's underlying here. So to get at that, this is sort of a placeholder figure. Basically, this is from Brandon's thesis. So we're constructing a big geologic model constrained by the seismic and the geology. So our seismic's here. And then what we want to do is combine that with all the geophysics, the lithoprobe and metal earth MT data, and of course, different layers of geophysical data. And we do have the 3D model already for the MT data. Basically, we're trying to put this into a big lithospheric scale model, and we're working on it right now to better outline this architecture at the broad scale. Okay, so just a quick sort of summary. We're sort of finishing up all the master's work, and PhD projects will be done soon. We're getting some of that submitted for publication and peer review. I should have 2 papers submitted on this work this year, at least. There's going to be some thematic work looking at the footprints of those big deformation zones, comparison to other areas. Me and Steph put in a TGI proposal to do some further modeling of the region. And so we're going to start synthesizing everything and getting it all out to the community to get a closer look at. So to conclude, the Southwest Superior Province records actually 1 billion years of Archean history. So it looks like we have good evidence for its origin in the Eoarchean. There's further stabilization of continental crust in the Mesoarchean in the Winnipeg River and Marmion. And of course, then we have the Neo-Archean history, which it looks like that formed in sort of a pericontinental setting, so in close association with these older rocks. And that really influenced the metallogenesis, because in places where there's a lot of this older, thicker continental crust, it really limited the endowment, whereas in other places separated by these translithospheric structures, we have more juvenile crust and actually a little bit more mantle inputs, and actually have some decent looking deposits on one side of those structures. So again, we're really focused on really building this architectural picture to help us better understand these controls that Metal Earth is trying to get at in terms of variable endowment. So thank you.
Great, thanks very much, Ben. We have time for a couple questions. Anything from the audience?
I have one, Ross, if I'm
Go ahead, Grant. Yep.
Yeah, nice talk, Ben. That was very interesting data. So what you found with hafnium signatures is very much in line with, we published a global compilation mid last year that shows, interestingly, so for the Paleoarchean rocks, they have rather chondritic values, but actually if you go back even further, when we compiled the 3.8 to 4GA zircons, they have more evolved signatures. And so actually there's a really interesting shift from the really old rocks, which are basically reprocessing, appear to be reprocessing crust in a very stagnant lid regime, to all of a sudden you get the appearance round about the time that you've identified here globally of these chondritic values, which appear to mark a shift to more mobile lid tectonics, however you interpret that.
Yes.
Where all right across the world, you've got this juvenile signature coming in. So I'd be tempted to be a little more cautious about, maybe a big supercontinent, but maybe think about more a change in global processes in terms of how how lithosphere is evolving in the early evolution of the Earth. But really great to see that that's exactly what we found in the rest of the compilations. But look, But make the compilation, make the comparison with the earlier rocks too. It's
yeah, I cut off this figure, so I actually have compiled data for Antarctica, Nuka-Waigatuk, Acasta, and of course Adrian's great data from all those places. So I have a C and a D panel that have some of those older rocks as well. Yeah.
I'll send you the paper we published in Geochemical Perspectives, which
that'd be great. I
probably not agree with the conclusions, but you can look at the comparison.
Yeah, and this is, I should clarify, this is only magmatic rock, only igneous rocks.
Yeah, no, sure. Yeah.
In this case.
Yeah. And then secondly, for the lithospheric architecture, I mean, also I would. It's interesting that we appear to sort of move to this idea that, there's this, you've got the juvenile magmatic input that may be driving the gold mineralization. And then to me, I mean, I then think about, okay, so what does that imply for deeper down? So to get that juvenile input, then you have to have very thin lithosphere at that time. You haven't got a 200 kilometer thick lithosphere, for instance. Otherwise, you're not going to get that juvenile input. So if you see our mantle group presentation on Thursday, I mean, that's sort of very much the interpretation we're moving towards, which may sound obvious, but it's not discussed in the gold metallogeny models. I mean, you can't have thick old lithosphere when you're sticking all that juvenile material into the crust at that time. Exactly,
and that's why we really think things like this Manitou, Norwick are really these. So it's probably like a synvolcanic. Or it's a extensional fault that breaks apart this old lithosphere and then lets in all this thin lithosphere. And then,
well, if there was any there to start with, Ben, I mean, it may be that the thick old lithosphere was actually generated in the Neo-Archean, so you don't even have to break it apart. So you might have thick old crust, absolutely. The question is whether you have the thick peridotitic mantle underneath. I don't think you did in the superior.
The subcontinental component.
Yeah.
Okay, guys. I think we're gonna have to cut it there. Thanks very much. Hey Ben, there's a number of comments there in the chat room for you as well. If you can.
Great. I'll look at those. Thanks, guys.